So let us continue the discussion on Zener regulation to some extent before taking up a new topic. So in the last class, please look at this diagram. In the last class, we have seen that by connecting a Zener resistance across the load resistance and then using a series resistance, let me call it as RS, with a full wave rectifier or half wave rectifier with a capacitor connected across it, we can get almost constant voltage at the output. Since the Zener characteristics, the reverse Zener characteristics is like this, when the voltage goes slightly beyond Vz, it allows a lot of current to flow through it. And because of this characteristics, it can be used in this particular application. When a capacitor is used, we know that the waveform of the voltage across the capacitor or at the output would be of this type, with a huge amount of DC potential and a small AC component around it. Now, if Vz is maintained at a lower level than these two voltage levels, then what happens is the Zener diode can accept varied amounts of currents. When the voltage itself is around Vz itself, it allows varied amounts of currents and sees that the additional voltage, which is in the form of the alternating component, gets absorbed across this resistance. So please recall the application where we have the voltage, application example where we have the input voltage varying between 11 volts to 12 volts, and with 10 kilo ohm resistance here and 10 volts Zener, this accepts 1 milliampere current, and when the input voltage is 11 volts, the Zener will accept 9 milliamperes of current, and the total current through this series resistance therefore would be 1 plus 9 equal 10 milliamperes, and the voltage drop across that would be 1 volt, and 1 volt plus 10 volts is equal to 11 volts. So that's what is the situation when the input is 11 volts. On the other hand, when the input is 12 volts, the Zener will still maintain almost 10 volts and it will accept 19 milliamperes through itself. That means the operating point now would be this, where the operating point earlier is this, with this as 9 and this as 19. Now, with the voltage remaining as 10 volts, 1 milliampere flows through this, and now the total of 20 milliamperes flows through it, and the voltage drop across the resistance would be about 2 volts. So 2 plus 10 amounts to 12 volts. This is how, by allowing varied amounts of current through itself, the Zener maintains almost constant voltage at its output. As a result, the ripple can be considerably reduced. So this is what a Zener diode, by using a Zener diode, we can achieve. Besides, or by the side of it, a Zener diode can also help in improving the regulation, voltage regulation. As we have seen, so regulation D is the percentage regulation of a circuit, so gives you how much, with what percentage the output DC voltage will vary or the output DC voltage varies with the different amounts of load currents. Now in this application, if we change this particular load resistance to say 5 kilo ohms, so that now the load is increased, let us consider it as 2 kilo ohms, so that the load is increased from 1 milliampere to about 5 milliamperes, with the provided the voltage remains constant at 10 volts. Let us see, by changing the load current from 1 milliampere to 5 milliamperes, whether the voltage remains constant or not. Now, by changing the load, what happens is, or by increasing this current, what happens is, whatever is the current that flows through the zener, whether 19 or 9, it gets divided as 5 and 5 milliamperes, or 5 and 15 milliamperes. Okay, and still the voltage would be 10 volts, and the voltage drop across this would be 1 volt when it is 11 volts, input is 11 volts, and it would be 2 volts when the input is 12 volts. So the current passing through the series resistance is the same, either 20 or 10 when it is 12 and 11 respectively. Okay, so the only difference being the zener current, some of the zener current will get redirected into this load resistance and maintains the output voltage at constant volts, 10 volts. How does it happen? Once again, the characteristics of the zener. With 10 volts plus a few millivolts itself, you can vary the current passing through it. Therefore, with minor variations of a few millivolts in this 10 volts itself, this current sharing takes place and the output voltage remains constant. Hence, to a good extent, this circuit provides almost a constant voltage with varying load resistance. Hence, regulation is good. The percentage regulation is low, and the voltage regulation capability of the circuit is good. Of course, this capability is limited, and if you make it up to what maximum load current you can proceed, up to the zener current. The zener current is, can at the most go down to 0, ideally, isn't it? If you try to reduce the resistance further and make it 100 ohms, so this 12 volts will get divided between this resistance and this resistance, and it will become 6 volts. When it is 11, this would be 5.5 and 5.5, and this voltage is less than 10 volts. Therefore, zener doesn't come into picture, and the zener is like an open circuit. Okay. Therefore, this percentage regulation doesn't go for any load current. Is not effective for any load current. So it will work at 10 volts as long as the operating point is on these characteristics. That means the voltages still remain 10 volts and some appreciable current flows through this. Current of the order of 1 milliampere at least flows through this. So that means under the minimum voltage, if you want to maintain 1 milliampere current through this, what is the current that is at the most can be drawn by this load resistance? It is naturally 9 milliamperes. That means the resistance is of the order of 1.1 kilo ohms. That is the smallest load resistance that can be connected here. If you want to increase the range of load, so you have to reduce this resistance to say further to say a 50 ohms, in which case the current flowing through the zener would be almost doubled. It will vary up to about 40 milliamperes. of 39 milliamperes. Okay, so this is how one can go about while designing the circuit. In practice, we see that at least a minimum of 5 milliamperes flow through the Zener. So that means the operating region is up to from 5 milliamperes and above. If the current flowing through the Zener can be varied between 5 milliamperes to 50 milliamperes, then the load variation can be also of the same order. If this can vary over one decade, the load variation also can be over one decade with the voltage, output voltage remaining constant. If you look at it microscopically, you will still find that there is a few millivolts of voltage variation. As a result, the percentage regulation is not zero actually. You will find some amount of very low percentage regulation. What is responsible for it? The slope of this characteristic is responsible for it. That RZ, the series equivalent resistance of the Zener diode. Please note that the equivalent circuit of the Zener diode is like this: RZ, RZ, and VZ. So because of this small RZ, so you will find that the voltage increases and decreases over VZ, but that is very small. Okay, but percentage regulation can be analyzed as a function of, it can be analyzed as a function of RS, RL, and C over here. So it can be analyzed. I'm not doing it here because it is doesn't fall under your syllabus, but please note that this can be very easily computed as an extension, derived, and an expression can be arrived at. Any questions on Zener regulation?
So what is the approximate waveform at voltage?
The approximate waveform is, if you look at it with the naked eye on the CRO, you will find a flat characteristics. But if you really look at it microscopically, so you will find that some variation of this type would be there. A few millivolts of this variation would be there. So naturally that variation is coming from the variation at the input. This is ripple because of the ripple over here, the same ripple at a much attenuated level, the same ripple appears in the output. But this time it would be of the order of a few millivolts.
So what is the order of RZ?
RZ is a fraction of an ohm. Typically it is a fraction of an ohm. 0.1 ohm, okay, 0.2 ohms, 0.5 ohms of that order. In fact, even less than 0.1 is also very common. Any other question? So with this discussion, we shall close our discussion on the rectifiers. And so let me discuss about another a few types of diodes which are very widely used in practice. So semiconductor photodiodes. So let me discuss about a photodiode. A photodiode is a p-n junction diode enclosed in a transparent plastic package or glass packaging. So you have a PN junction diode inside. With the two terminals coming out, and this diode is enclosed in a transparent package. And when light is made to impinge on this PN junction diode, its characteristics changes. So what kind of changes do you expect in the characteristics? So this is the kind of characteristics we expect. It is usually operated in the reverse direction with negative potential applied. And it gives different amounts of reverse current, and with the characteristics exhibited in this fashion. With light intensity given in this fashion. This is dark current. So here the light intensity impinging on the diode is 1000-foot candles. This is 2000-foot candles, 3000-foot candles, and so on. So this current is of the order of say 200 microamperes in a typical diode. So this is about 300 microamperes. This is about 100 microamperes, and so on. So it is usually operated in the reverse direction under reverse bias. So this is the kind of characteristics a photodiode exhibits under reverse bias. But first let us understand the characteristics, and then we shall get into the physics of it. We shall understand the working of it. Please note that a PN junction diode under reverse bias gives you a reverse saturation current, this I0. So this is due to the minority carrier flow to the diode. So this is of the order of a few nanoamperes in the case of silicon diode, and it is of the order of a few microamperes in the case of a germanium diode at a normal temperature. Now, when light is made to, that means when the diode is sealed inside an enclosure where light doesn't pass through. When then the characteristics is like this, like a typical PN junction diode. Now, when light is made to fall through that, what happens is the reverse saturation current increases. So the reverse saturation current now is this much. This is the reverse saturation current. Now with the light intensity increase, the reverse saturation current is increased to 2000-foot candles. The reverse saturation current is this much. And with 3000 is the reverse saturation current. Of course, the reverse current approaches the reverse saturation current with increased reverse potential. As the reverse potential decreases, the reverse current goes down. So we know that the diode characteristics, VI characteristics, is given like this. So I is equal to I0, the reverse saturation current, when the reverse voltage is very large. So V is of the order of say -5, -10 volts. Then, so this is I is equal to -I0. when the reverse voltage is less, of course, this would be less than I naught, and this is the characteristic. This is how it goes. Now, with light emitting, with light impinging on the junction, it is like this. The characteristics goes like this. So that's how the characteristics is. So please note that the light intensity is measured in terms of lumens or foot candles or watts per meter square, because light is equivalent to energy, and the light intensity is measured in terms of energy per square meter. Therefore, watts per square meter or foot candles or lumens per square foot are the units used for it. Now let us look into the physics of it and how it happens. When light impinges on a p-n junction, the whole electron pair concentration increases because of the additional energy being supplied. So its temperature rises and the light energy is passed to the electrons, and more number of electrons go out of the valence bands, and as a result of which the whole electron pairs are generated. And because of the additional number of whole electron pairs that are generated, in addition to the thermally generated whole electron pairs, you have the increased minority carrier current concentration, because of which the reverse saturation current increases. So when the reverse saturation current increases, I increases. Even for slight amount of positive potential, so you will find some amount of reverse current that is passing through because of the diffusion phenomenon, diffusion of the minority carriers. When the population increases, diffusion takes place apart from drift. For the charge carriers to drift, you need a potential difference. Even when the potential difference is 0, you will find some amount of current because the minority carriers diffuse across the junction. So can the majority carriers diffuse across the junction? For the majority carriers to diffuse across the junction, there is potential barrier. Therefore, once the equilibrium is established, the majority carriers cannot diffuse. Now, because of this light exposure, the minority carrier concentration is increasing, and once the concentration is high and there is no barrier for it, so therefore they diffuse across the junction. Due to the diffusion, you have, even at 0 reverse potential, you have some current flowing in the reverse direction. Now, if you plot the current versus the intensity of the light, the characteristics, it is almost proportional to the light. The current is proportional to the light intensity in foot candles. So this is of course equal to the dark current. When the intensity is 0, we have some current, that is the dark current, which is equal to the reverse saturation current of a p-n junction diode. But as the light intensity increases, current increases proportionately. So what are the applications of such systems? In an assembly line or in a plant, when where you have material passing over the conveyor belt, either finished products or some material passing over the conveyor belt. You can use sensors of this type and then count the number of units that passes by. You have a light source here, and you have on this side a photodiode. And have it in a circuit. Now when there is no obstruction, this light falls on the photodiode and you have current passing through. Now when this unit goes here and obstructs this light, you will have the current obstructed, and the current goes down from typically say that 200 say microamperes to it goes down to say 1 microampere to the dark current level, because the light intensity, the light falling on this is obstructed. So in which case for every unit that passes this light, you will have a pulse of this kind generated. So the current across, the current through the PN junction diode would be like this. Then if you pass this current through a resistance, you have a voltage of this type appearing across the resistance. If you further amplify it, use an amplifier, you have a sizable amount of current voltage pulses appearing like this. Then pass it through a counter. After amplification, you pass it through an electronic counter. We will be discussing about the counters towards the end of this course. And the counter gives you the count out. So the number of obstructions that have taken place, that means the number of units, so that they passed over the conveyor belt. So many such applications are there where you can use this the photodiodes. Another very important application is the optical communication, where we have optical fibers laid between one end of a communication system, at the transmitting end of the communication system, and the receiving end of the communication system. If the signals, either a video signal or audio signal or several lakhs of audio signals, or means voice signals, telephone signals, are multiplexed together, they can be transmitted on the optical fibers as on-off pulses. Light intensity is turned on and off in digital form. Then at the other end, if you introduce a photodiode at the other end, the photodiode will give you these on-off pulses. When there is light, it gives you an output. When there is no light, it gives you the dark output. And from this, one can get the signal back. It is very widely used in optical communications. Any questions on photodiodes? Optical communications. Actually, optical communications, you have optical fibers, which are basically glass fibers, and you can pass light through such fibers. So light can be passed through them, and with some amount of attenuation, so you get the light pulses on the other side. So typically about you can pass light through a fiber over say 100 kilometers typically, and if you with a torch you make it on and off this light, so you have on and off kind of light on the other side, but the intensity would be slightly reduced because of the signal getting attenuated over such a long fiber. So you can lay this fiber in the ground, so it does permit some amount of bending also. So the light passes through it and then goes over the other end. So you can send signals over it. In optical communications, actually thousands of speech signals or lakhs of speech signals are multiplexed and they are sent through these optical fibers. And on the other end, you can have you can demultiplex them and get back the lakhs of signals, lakhs of voice signals. It has a very huge capacity, bandwidth capacity. It can take several TV signals and several, lakhs of audio signals, speech signals to the other end. We have such optical fibers across oceans, through submarine optical cables, and on land. And in our institute, we have an optical communication computer network in our institute that is an ATM network. At the physical level, the signals go through a fiber, optical fiber. Okay, any other question?
If we expose any reverse bias PN junction diode to the light, do we have increased reverse current?
Provided you have the construction is such that it allows, there is a glass enclosure and it allows the light to go through directly. Yes, it does. But if you have painting on it and the construction is such that the junction is very much within inside, and you have some other coating, some other material coating over it. Otherwise, yes. You heat it, the current increases. With rise in temperature, the reverse current increases. That's because heat goes there. If it is sealed, of course, naturally, as I said, it doesn't.
So there should be a breakdown voltage for photodiode also.
Yes, there is. It breaks down naturally.
Is that made use of in any way?
The not particularly as a photodiode, but every diode breaks down and we are using it. Zener diode is an example.
But is it using light?
No, there is not much of change in that. Therefore, so it doesn't. It is not used typically. Another question? Now let us discuss about a light emitting diode. So light emitting diodes. The light emitting diodes are, so those diodes which when biased gives you light. So the light emitting diodes give you light when it is biased. Depending on the construction, you can have red, green or yellow kind of light coming out of the diode junction. The volt ampere characteristics of such diodes is like this. So this is the typical volt ampere characteristics of such a diode. At almost at 1.5 volts, the current is almost zero. When the current becomes appreciable, which is of the order of 5 to 10 milliamperes, you have light coming out of the diode. But as far as the terminals are concerned, the volt ampere characteristics is as shown here. Okay, so typically around 2 to 2.5 volts. When you apply around 2 to 2.5 volts across the diode, it gives you light. And how does it happen? In a forward junction PN junction diode, and when it is forward biased, so we know that holes, which are the majority carriers on the P side, diffuse to the N side, and the electrons from the N side diffuse into the P side. And they diffuse. As the diffusion proceeds, what you have is the whole concentration on this side increases, and you will find that the whole concentration goes down like this. And on this side, the electron concentration goes down like this. That means the injected holes recombine with the electrons, and the concentration goes down. When you have more number of electrons which are present here, if the holes are injected from outside, what happens is they recombine, and in the process the concentration goes down with distance. But the current anyway takes place because the charge passes, therefore current would be present. The concentration of charge carriers of course goes down in this fashion, but the total remains almost constant. Now because of the recombination here, the electrons from the valence band are jump back to from the conduction band, jump back to the valence level to form the covalent bonds. And when they jump back, so they emit energy, and they pick up energy, the thermal energy, and they go into the conduction band, and when they go back to the conduction band, they emit energy. And normally what happens to this energy? This energy gets dissipated as heat in the body of the semiconductor. Now by construction of the semiconductor, if you see that, so this energy comes out as light. You can have light coming out of the junction diode. So this happens when you use materials of the order of materials of the type gallium phosphide and gallium arsenide. So when you have the diodes constructed using semiconductors like gallium arsenide and gallium phosphide, you have this kind of light emitting outside the diode. So that happens because of the recombination of holes and electrons. For the holes getting recombined with electrons on this side, and with the electrons recombining with the holes on this side, so this light emits. And the construction should be such that in the junction you have a huge area to emit light outside. There should not be any obstruction. So such diodes are known as light emitting diodes. And with the intensity, with current, the intensity of light, so that goes out, is like this, it varies like this. If this is the light relative intensity of light, and this is the forward current. So at 5, 10, 15 and 20 milliamperes, this is these are the typical operating currents. Then the intensity would be so varying like this, relative intensity, and the absolute intensity depends on the type of diode. We have very bright LEDs and we have faint LEDs also. And these LEDs are very widely used in instrumentation. You have instruments with LED displays. You have the LED displays in the advertising world. The huge LED displays displays information, advertisement information in some city corners, city centers. Okay, and in the instruments also you have seen the electronic instruments and non-electronic instruments with LED displays, digital displays, giving you light. You have another type of displays known as the LCD displays, which are different from LEDs. Okay, so LCD is the liquid crystal display. So LED is a light emitting diode display. Okay, so then we shall discuss about the next topic in the coming class.